Good evening, dear colleagues. Thank you for this opportunity to present my work. Entitled Effect of the Laser Shock Peening Area Allocation on the Fatigue Properties of Specimens with Stress Concentrators. I think my colleagues said enough about what laser shock peening is, so I can skip this part of my presentation. And I want to note that laser shock peening has many different parameters, which may have different impacts on its efficiency. So this work focused on one of the key factors, the position of the treated area relative to the stress concentrator, and how it affects the fatigue behavior of titanium flat titanium specimens with stress concentrators. So, and a little bit more about our complex for laser shock peening. It is first complex in Russia of laser shock peening, and we really proud of it. Several years ago, our institute developed an experimental facility for implementing the laser shock peening process, and its main components are shown on the slide. The workflow begins at the operator station in operator position, where a dedicated software package is used to create processing programs. These programs are uploaded to the controller of robotic manipulator with payload up to 50 kilograms. Yeah, okay. Robotic manipulator, which enables automated treatment of components with arbitrary geometry. After mounting the specimens, an optical focusing system is installed. You can see these optic systems in the center of this slide. This system includes three lenses that produce laser spot on 2 millimeters diameter and 1 by 1 and 3 by 3 millimeters square. This optical system is positioned in a window between the adjacent room. One houses the processing chamber, and the other contains the main element of this complex is pulsed laser with maximum energy in this pulse up to 10 joules. Before processing, two nozzles are aligned, one supplying water, which we use as a confining layer, and the second providing air to protect the optics from small parts of aluminum foil, which we use as a protective coating, water, or some dust. After treatment, we measure residual stresses using the automated system MTS 3000 Tristan. And a little bit more about this system. We measure residual stresses using the whole drilling strain gauges method in accordance with the international standards ISTM E867. Strain gauge with three measuring grids, you can see it on the figure 4, is installed on the surface of the specimens. In the center of this gauge, a hole with a diameter of 2 millimeters is drilled. Drilling is carried out step by step, and in the end of each step, we recorded the values of the hole deformations. Based on this data obtained, we inverse problem, and we solved the inverse problem, and residual stress received residual stress profiles. So that's what about our equipment. As for the specimens which we use in these experiments, there was two types of flat specimens. First was made from titanium grade 2 with a V-shaped notch, and the second was made from titanium aluminum molybdenum with semicircular notch. You can see their geometries on the figure 5 and 6. The fatigue properties were studied, like Aleksei said, using the BIS, the severe hydraulic testing machine, under condition with an axial cyclic deformation with a cycle asymmetric coefficient 0.1 and a maximum cycle load on 8 kilonewtons. Crack length monitoring during the fatigue test was performed using the potential drop method, which enable continuous real-time taking of crack growth. A little bit more about this method. Paired electronic contacts were welded onto the specimen surface. A constant current was applied through the machine grips, and the voltage drop between the contacts was measured using a different amplifier and digitalized for further processing lab view. It's about our experiment with titanium grade 2. The laser shock peening parameters you can see on the screen. We investigate two different schemes of location laser shock peening zone. First scheme, laser LSP zone positioned 1.5 millimeters away from the notch. And scheme number 2, LSP applied directly around the stress concentrator. It's figure 11. It's figure 8. Right after laser shock peening, we measured the residual stresses to understood what we have after using different laser shock peening zones. As you can see on the screen, we have the similar picture. If you speak about maximum values of residual stresses and its depth for both schemes. So we think that at the beginning of the fatigue test, both specimens has initially the same residual stress state. So in this slide, you can see the fatigue crack growth, the results of fatigue crack growth monitoring. For specimens treated according to scheme 1, crack initial earlier than the untreated specimens, and their propagation rate was higher. This behavior is attributed to the presence of tensile residual stresses surrounding the treated zone. While compressive stresses was performed 1.5 millimeters away from the notch, the region immediately adjacent to the notch contained tensile stresses, which accelerated crack development. By the time the crack approached the compressive region, the stress intensity factor had already increased to the level and which the compressive stresses could not longer efficiently retard crack growth. Unlike scheme 1, the specimens treated according to scheme 2 demonstrated a pronounced improvement of fatigue behavior. And you can see it in the figure 12b. They crack length curves show that crack initiating being significantly delayed compared with the untreated condition. During the earlier stage of loading, the crack did not grow, indicating that compressive residual stresses formed directly around the notch effectively reduce the local stress intensity. And the crack growth rate diagrams is figure 13 further confirm this effect. And finally, the fatigue test results for these specimens from titanium grade 2. Analysis of this diagram showed that the first treatment scheme negatively impacted the fatigue properties of the V-shaped notch specimens, as the number of cycles to failure decreased by 30%, compared to untreated specimens. And specimens treated with the scheme 2 showed a roughly two-fold increase in fatigue life. And following this, similar tests were conducted on titanium alloy specimen from titanium aluminum molybdenum. But here we use only one scheme. It's scheme number 2, because we know that this scheme was better than the scheme number 1, and we had similar results as we investigate the specimens from titanium grade 2. They demonstrated improved fatigue life after laser shock peening. Crack initiation was delayed, and crack growth rates were reduced compared with untreated conditions. And fatigue tests showed us the similar results. We see that fatigue life increased up to 85% after laser shock peening. And here you can see the main conclusion of this work. The location of the laser shock peening treatment zone is the key factor governing the fatigue life of notched titanium specimens. Applying laser shock peening directly around the stress concentrator yields a substantial increase the fatigue life, average more than 100% for the material studied. When the treated area is shifted away from the notch, surrounding tensile residual stress may accelerate crack initiation and growth, leading to a reduction in fatigue life. And for the investigated laser shock peening parameters, the dominant beneficial effect associated with delayed crack initiation, whether the crack growth stage is less affected. And that's all. Thank you for attention.
Thank you.